Hi guys, Happy New Year 2024. I welcome you to my YouTube channel, Learn Physics with IBM. One of my students asked me to record May, June 2023 papers because there are so many concepts they don't understand. So today I decided to get some time and record these papers. So straight away, let's go to the question papers. Remember, question paper 4.1 and 4.3 are the same. So I'm only going to record 4.1 and 4.2. So without wasting time, I would like to take you to the question papers. So I will start with question 4.1, and the student's name is IBM. So you can read through the instructions. You are used to these instructions. So I will just go straight to the questions and start answering them. This paper is supposed to be 2 hours. I'll try my level best, but because of explanations, I may take more time. The paper is 100 marks. And this is the most important paper. If you are sitting for both AS and A levels, this is the paper you should give more emphasis. So without wasting time, I'll not go through the quantities given, the constants. We are used to these ones. You can't follow this video without printing the question paper. So question number 1, define gravitational field strength. So we know that gravitational field strength is the force acting on a unit mass. So it is simply the force per unit mass. Force per unit mass. The force acting on a unit mass is what we call gravitational field. That is the force per unit mass. But to understand what we really mean by gravitational field, we may not really define it as the force per unit mass. The best definition for gravitational field would be, because the field is a region of space, where a mass, a charge, or anything experiences a force. Then we would define gravitational field as a region where a mass experiences a force due to another mass. That is what we really mean by gravitational field. But sometimes people will define gravitational field as force per unit mass but essentially they would be defining gravitational field strength instead of gravitational field. So a region of space where a mass experiences a force due to another mass is what we call a gravitational field. But the force per unit mass is actually the gravitational field strength. So sometimes people want to think that gravitational field and gravitational field strength are the same thing. So sometimes it is considered to be the same thing, but essentially the best definition for a field, because a field is a region of space where a force is experienced, then a gravitational field is a region where a mass experiences a force due to another mass. And then define electric field. So this one is also going to be a region of space where a positive charge, a unit positive charge, experiences a force. That is what we call an electric field. So a region of space. A region of space where a charge experiences a force. A region of space where a charge experiences a force. That is what we call an electric field. Now, some people may want to define an electric field as force per unit charge, but that is really per unit positive charge, but that really doesn't make any good sense, saying that an electric field is the force per unit positive charge. Essentially here they would be defining electric field strength, but both of these would be acceptable. A region of space where a charge experiences a force is what we call an electric field. Although many times the electric field acts in the direction in which a positive charge moves, people would wish to define an electric field as a region of space where a charge experiences a force. Okay, state one similarity and one difference between the gravitational potential. This is normally represented with the letter phi, and electric potential, which is normally letter V. So let's begin with the similarities. If you recall, you remember that gravitational potential phi was equal to negative Gm divided by R, and electric potential V was given by Kq divided by R, where R is the separation or the distance from a fixed point, yet for gravitational potential is the separation between the two masses. So one of the similarities is that they are both inversely proportional to the distance from a point. So both inversely proportional to the distance from a point or from the point. They're both inversely proportional to the distance from the point. Remember, potential at infinity is defined to be zero. So, and this is true for both. So we can say it is zero at infinity. It is defined to be zero at infinity or at infinite distance for both. Gravitational potential is defined to be zero at infinite distance for both. That's why you see we have a minus for gravitational potential, because if potential at infinity is zero, yet the force between the two masses is attractive, then that means potential elsewhere is going to be less than zero. And if you recall also that if you recall the concept of equipotentials, if this is an equipotential surface, then a point here and a point here on the same surface are the same potential. So we can simply say that points of equal potential lie on concentric spheres. Points of equal potential lie on what we call concentric spheres. So, but of course, the first two are very common, inversely proportional to distance from the point. That one you can see it from the formulas. Remember, G is the gravitational constant, and K is the constant, which is 1 over 4 pi epsilon naught. And potential is zero at infinity for both. Then the difference is the most important difference is that gravitational potential is always negative. That's why you see that in the formula I must include the minus. Electric potential can be positive or negative. So that is the most common difference. So I will simply say gravitational potential is always negative. The reason as to why it is always negative is because two masses never repel each other. The force is always attractive. But yet for charges, like charges repel, unlike charges attract. So the electric potential can be positive or negative, depending on the signs of the charges involved. So that is the difference. The isolated uniform conducting sphere has mass capital M and charge capital Q. The gravitational field strength, this is the force per unit mass, at the surface of the sphere is G. The electric field strength, this is the force per unit charge, at the surface of the sphere is E. Show that M over Q is equal to alpha times G over E, where alpha is a constant. Okay, so by definition, gravitational field strength G as being force per unit mass, per unit test mass. This one is the same as capital G, capital M over R squared. That one we know. Also, we know that electric field strength, which is the force per unit charge, for a point charge, the electric field strength is given as Q divided by 4 pi epsilon naught R squared. We know this one, so I'm going to combine these two by dividing. If I divide G over E, this is going to be equal to capital G, capital M over R squared times, because I'm dividing, I'll get the reciprocal. So this is 4 pi epsilon naught R squared divided by Q. So we notice that R squared has cancelled out. So it means the ratio G divided by E is actually going to be capital G, capital M times 4 pi epsilon naught divided by Q. So if I try to do the math, I have that I want to make M over Q the subject. So I have that G over E is equal to M over Q, then times 4 pi epsilon naught times capital G. So I want this one to be the subject. So it means capital M over Q is going to be equal to G over E divide by, so I'm dividing by 4 pi epsilon naught G, which is the same as times 1 over 4 pi epsilon naught G. Remember, 4 pi is a constant, epsilon naught is a constant, G is a constant. So it means 1 over 4 pi epsilon naught G is equal to alpha, which is the constant at this point. Hence, I just conclude that M over Q is equal to the constant, which is alpha, times G divided by E as required. So that is the simple question there. Show that the numerical value of alpha is 1.35 times 10 to the power of 20. So alpha, we have already seen that the constant alpha is 1 over 4 pi epsilon naught times G. So I'll just substitute the quantities because they are given in the list of formula. If you have done this, you are used to these quantities. So this is 4 pi times epsilon naught, which is 8.85 times 10 to the power of minus 12. You can check in the list of constants. Then times G, which is the gravitational constant, which is 6.67 times 10 to the power of minus 11. You can also check this in the list of constants. So calculator. So from my calculator, I have that 1 divided by 4 pi times 8.85 exponent minus 12. I know when I add here, it will not make. Okay, so I'll use two brackets. So I have 4 pi. Okay, let me put 4 pi outside. 4 pi into the first bracket, 8.85 exponent minus 12. Then the second bracket I'll put 6.67 exponent minus 11. Close that bracket, then close the outer bracket. So when I press my calculator, I'm getting 1.38348 times 10 to the power of 20. So this is what they wanted us to show. Assume that the Earth is a uniform conducting sphere of mass 5.98 times 10 to the power of 24 kilograms. The surface of the Earth carries a charge of minus 4.8 times 10 to the power of 5 coulombs. That is evenly distributed. Use the information in the bit to determine the electric field strength at the surface of the Earth. So they have given us an expression that G divided by E or M over Q is equal to alpha times G over E. M over Q is equal to alpha times G over E. So we want to use the information to determine the value of E, which is the electric field strength. So if I make E the subject, I have that E is equal to alpha times G times Q divided by the mass M. So I'm just going to substitute. E is going to be equal to alpha. We have already got alpha as 1.35 times 10 to the power of 20, rounded off to 3 significant figures. G is the gravitational field strength. Since we are on the Earth, G is 9.81. So this is times 9.81 times Q. They have given us the charge as 4.8. So I will not include the minus. So this is 4.80 times 10 to the power of 5. Then divide by the mass. So the mass is 5.98 times 10 to the power of 24. So I'll check my calculator. 1.35 exponent 20 times 9.81 times 4.8 exponent 5 divided by 5.98 exponent 24. So I'm getting this as 106.3. 106.3, or approximately to 3 significant figures. I'll just write 106. What are the units of electric field strength? That is volts. It can be volts per meter. It can be newtons per coulomb. If you remember from uniform electric field, E is force per unit charge. That is newtons per coulomb. E is also equal to V over D, which is going to be volts per meter. So any of these could be the units. So I'll write here one of them. I'll say newtons per coulomb. Coulomb is a capital letter, so I have corrected this. Newtons per coulomb, or it is volts per meter. State how the direction of the electric field at the surface of the Earth compares with the direction of the gravitational field. Electric field at the surface of the Earth, we are seeing that E is equal to, they say direction, not magnitude. But of course, we see that the magnitude is many times bigger than, it's going to be many times, because G is 10, gravitational field strength is 10, and electric field strength is 106. It means it is many times greater. It is about 10 times or 11 times, or approximately 11 times. So state how the direction of the electric field at the surface of the Earth compares with the direction of the gravitational field. So first of all, the gravitational field is attractive. But then here they said, assume that the Earth is a uniform conducting sphere of this mass. The surface of the Earth carries a charge minus 4.8. The surface is carrying a negative charge, and yet electric field strength is due to a positive charge. So if this is the Earth and it is carrying a negative charge, so the Earth is a negative charge. To define electric field strength at a given point P, we always imagine a unit positive charge here. So if this is the Earth, which is a negative charge, and we want to find electric field strength at a point from the Earth, because the Earth is negative and we always imagine a unit positive charge at the point we want to consider, we notice that the force will be towards the Earth. The force is towards the Earth. That means the direction of the field is towards the Earth. Yet if you consider the gravitational field, if we consider this being the Earth, and I put a mass here, a unit mass at this point, of course I can't put a positive mass. So, and this is the mass of the Earth, capital M. Considering the mass here at point P, the force is always attractive. So in both cases, the force is attractive. So it means they are going to be in the same direction. So same direction. However, if the Earth was considered to be carrying a positive charge, then the electric field here would be in the opposite direction. It will be repulsive. So you must note that very carefully. It is in the same direction because the Earth is carrying a negative charge. And if we imagine a positive charge at point P, it is going to be attracted towards the Earth. Yet the mass of the Earth would attract another mass. This is for the gravitational field. This is for the electric field. So the mass of the Earth would attract another mass. So they are always going to be in the same direction. Okay, I think I've tried to explain that. Question number 2. A steel sphere of mass 0.29 kilograms suspended in equilibrium from a vertical spring. The center of the sphere is 8.5 centimeters from the top of the spring as shown in the figure. Okay, so if here this is equilibrium, the forces acting at the tension upwards, I'll call this one T1, and the weight downwards, which I'm going to call W. So in this case for equilibrium, T1 is going to be the weight, which is equal to mg. And this will be automatically 0.29 times 9.81. That is for equilibrium. T1 is equal to 0.29 times 9.81. The sphere is now set in motion so that it moves in a horizontal circle. Okay, if it is moving in a horizontal circle, which forces are then acting? Number one, the force keeping it in motion in the horizontal circle is the centripetal force, which acts towards the center. And of course, it has the weight, which acts vertically downwards. So there are two forces acting in the on the sphere. So if I resolve that, there must be tension here. I'll call this one T2. So the tension T2 will be tension T2 has two components. There's one in the vertical and one in the horizontal. The horizontal component is the one which provides centripetal force, and the vertical component is the one which balances with the weight. Of course, for equilibrium in the horizontal, by Newton's second law, the centripetal force acting towards the center could be balanced with another force that side, and the tension upwards could be balanced by the resultant of these two in the other direction. Okay, so the question is the distance from the center of the sphere to the top of the spring is now 10.8 centimeters. It means the tension must have increased because the spring is now stretched. Explain with reference to the forces acting on the sphere why the length of the spring is in the figure is greater. I say the tension must have increased, but remember the only forces acting here are the weight and the centripetal force. So I will say that the horizontal component, the weight of the sphere is now equal to the vertical component of the tension, that is for equilibrium. The vertical component will be this component here, T2 in the vertical is equal to the weight. So I will say the weight of the sphere is now equal to the vertical component of the tension. So the weight is now equal to the vertical component of the tension. And of course, the horizontal component of the tension provides the centripetal force. The horizontal component of tension causes centripetal force, or the horizontal force on the sphere causes centripetal force or centripetal acceleration. Causes a centripetal force. Just put acceleration. Okay, centripetal force stroke acceleration. Therefore, if we combine the horizontal and the vertical component, the horizontal and the vertical component therefore will give us a greater tension than before. So the horizontal and vertical components, the horizontal and vertical components of force now combine to give greater tension in the spring. The horizontal and vertical component, therefore, because remember the weight of the object is not going to change. And remember it was equal to mg, but now there is another force providing the whole centripetal force. So when you combine the centripetal force and the vertical component or the weight, the resultant is going to be a bigger force, a bigger tension in the spring. That's why I'm saying that the horizontal and the vertical components of force now combine to give a greater tension in the spring. Hence, if the tension is greater by Hooke's law, tension is equal to K times X. So if the tension has increased, then the extension must increase. Hence, giving a greater extension. Of the spring. So this will give a greater extension of the spring. Okay. The angle between the linear axis of the spring and the vertical is 27 degrees. Show that the radius of the circle is 4.9 centimeters. The angle between the linear axis of the spring and the vertical is 27. So let's go back here. The linear axis of the spring, the angle between the linear axis of the spring and the vertical. So this is the angle they're talking about, is given as 27 degrees. They want us to show that the radius R of the circle is 4.9. So this angle is still 27 degrees. And they want us to show that the radius is that. Okay. So I'll just consider something very simple. I'll just take out a triangle. From that, there's a vertical. There is a radius, and there is this one here, and this angle is 27 degrees. This is the radius. So the new length, remember, the length of the spring became 10.8 centimeters. So they want us to find the radius. So that is trigonometry. I'll simply say that sine of 27 is equal to opposite divided by hypotenuse. So it means R. Remember, this was the spring. So R is going to simply be 10.8 sine of 27. So I will press my calculator. 10.8 sine of 27. So that is 4.9 centimeters. Show that the tension in the spring is 3.2. Tension in the spring is 3.2. So remember the vertical component of, if you recall, we had here a weight vertically downwards, and we say the vertical component is equal to the weight downwards. So I have to resolve vertically here. So T in the vertical is actually going to be T2 cos of theta, which is cos of 27, because if this angle is 27, this angle is also 27 degrees. So it is T2 cos. Remember I said the tension here is T2. So it is T2 cos 27, which is equal to mg. But remember the weight was mg, which was 0.29 times 9.81. So in equilibrium, T2 cos 27 should be equal to 0.29 times 9.81. So I'll just substitute it here. So the tension, which I called T2 cos of 27, should be equal to the weight, which is mg. So I'm saying T2 is equal to the weight, which is 0.29 times 9.81 divided by cos of 27. So I just press my calculator. 0.29 times 9.81 divided by cos of 27. So this is giving me 3.19, which is approximately 3.2 as required. The spring obeys Hooke's law. Calculate the spring constant in newtons per centimeter of the spring. Newtons per centimeter. Okay. So if the spring obeys Hooke's law, remember Hooke's law states that the force is equal to K times X. This time the force will be the tension. So we can simply use I would get two equations, but I don't want to do that. So let the force be the tension being equal to K times X. There has been a change in length, which is directly proportional to the change in tension. So I'll simply say the change in tension is equal to the constant K times the change in length. So I may want to find the constant K. So the constant K is going to be equal to the change in tension divided by the change in length. So what is the change? Of course, change in length, that is the extension. So what is the change in tension? The change in tension, the new tension T2 is 3.2. T1, remember, was equal to the weight, which is 0.29 times 9.81. So I'll simply say 3.2 minus 0.29 times 9.81 divided by the change in length. Of course, the extension is change in length, so let me just say change in L rather than change in X. The change in length is going to be 10.8 minus 8. I think the original length was 8.5. Remember, this is in centimeters because we want our answer to be in newtons. This is in newtons. The other one is in centimeters. We want our answer to be newtons per centimeter. So this is going to be 3.2 minus 0.29 times 9.81. divide by 10.8 minus 8.5. So this is giving us 0.154. So this is 0.154 newtons per centimeter to three significant figures, or you can write 0.15. Use the information in B to determine the centripetal acceleration of the sphere. Remember from your concepts of circular motion, centripetal force is mass times centripetal acceleration. And remember, the centripetal force was the force in the horizontal. We had to resolve this in the horizontal. When I resolve T2 in the horizontal, it will be T2 sine of the angle. If it is cos in the vertical, if I use the vertical angle of 27, the angle here is 27 and it is cos, then elsewhere it will be sine. So that will be T2 sine of 27. That's what provides the centripetal force. So this means I will simply say that centripetal force is mass times centripetal acceleration, which is going to be T2 sine of the angle in the horizontal, which is sine of 27 if I resolve in the horizontal. That means the centripetal acceleration is going to be T2 sine of the angle, which is 27, divided by the mass. Remember, I would have used the angle 90 minus 27, which is, I think, 53. So that will be cos of 53, but I want to use sine. So this is going to be T2, we calculated it as 3.2 sine of 27 divided by the mass, which mass was given as, I think the mass was 0.29. Is the mass 0.29? Yes, the mass was 0.29. So I'll just press my calculator. 3.2 sine of 27 divided by 0.29. So this is 5.0. So the mass, the centripetal acceleration is 5.0 meters per second. Then calculate the period of the circular motion of the sphere. We want period. If you recall, centripetal force is mv squared over r, which is mass times centripetal acceleration. So it means the centripetal acceleration is v squared over r. I want you to also recall that v is omega r, and also recall that omega is 2 pi over t. So this is 2 pi divided by t times r. Okay. So it means the centripetal acceleration is going to be, I'm substituting for v squared. So it will be, when I square, I'm squaring this. So this is going to be anyway 2 pi r over t, but this is squared. Then divide by r, which becomes 4 pi r squared over t squared times r. One r is cancelled out. So it means if I make the period the subject, it means that the period, okay, t squared is going to be equal to 4 pi times r divided by the centripetal acceleration. When I find the square root, it means the period is going to be 2, oh, by the way, this was squared, 4 pi squared. So it will be 2 pi, that is square root, radius, divided by the centripetal force. So now I just substitute. So substituting here, I'll have 2 pi square root of the radius, which we have got as 5.0. Is it 5.0? No, this is centripetal acceleration, not radius. What was the radius? So I'm looking for the radius. I don't remember. Okay, the radius is 4.9 centimeters. We change it to meters. So the radius is 4.9. When you change it to meters, 4.9 divide, it is 4.9 times 10 to the power of minus 2. Change it to meters. Then the Centripetal acceleration we have got as 5.0. So I'll just press my calculator. 2 pi root 4.9 exponent minus 2 divided by 5. So the answer is 0.622. So this is 0.622 seconds. So that is question number 2, and I think that is the end of question number 2. Question number 3, state the reason why two objects that are the same temperature. Same temperature means no net flow of thermal energy will occur because they have the same temperature. There is no temperature difference. Energy, there will be flow of energy in all directions, but equally. So I'll simply say at the same temperature, at the same temperature, at the same temperature, there is no net thermal energy transfer or no net. This is the most important point. No net thermal energy is transferred between the objects. Between objects. It doesn't mean that there is no flow of energy. There is flow of energy equal in all directions. So because it is equal in all directions, there is no resultant flow in any particular direction. That's why I say the word net is the most important point here. Figure 3.1 shows the variations in the temperature of the densities of mercury and of water between 0 degrees Celsius and 100 degrees Celsius. Temperature may be assumed using the variation with the temperature of the density. Okay, so just why for measuring temperature over this temperature range, mercury is suitable. So you see that for mercury it is a straight line, which means temperature varies perfectly linear with density. Yet for water it is not a straight line. So I will simply say variation of density with the temperature is linear. The variation of density with the temperature is linear throughout. Is linear throughout. And what is the impact of this? It means that the temperature will have a unique value for each density. So temperature, so each temperature has a unique value of density. Because the variation of density with temperature is linear, it means each temperature will have a unique value of density. But let's look at water. Look at this point here and this point. It means you have two. At 0 degrees Celsius, the density is this, and at another certain temperature, the density is the same. It means temperature. It means for the same density, we're having two values of temperature, so it cannot be a good. It cannot be a good liquid for measuring temperature. Water is not a suitable liquid. So we see that the variation of density with temperature is not linear, but because this is 2 marks, it means we have to give more explanation. Two different different temperatures could be having the same density. So we shall say variation of density with the temperature. Variation of density with the temperature is not linear. And different temperatures have the same density. So from the graph, we see that there will be temperatures that will have the same density. There will be different temperatures that would have the same density. So it means this is not a suitable liquid for measuring temperature. There is a region where the density does not vary with temperature, or does not vary linearly with temperature. Okay, next, a beaker contains a liquid. The beaker contains a liquid of mass 120 grams. The liquid is supplied with thermal energy at a rate of 810 watts, that is power. The beaker has a mass of 42 grams. So this is liquid, this is beaker. Specific capacity of 0.84 for the beaker. The beaker and the liquid are in thermal equilibrium. That means there's no net flow of energy in any particular direction. So at thermal equilibrium, they are the same temperature. The figure shows the variation with the time of the temperature of the liquid. So let's see the figure. Okay. So we see that the temperature increases, then it remains constant at this level here. The scale here is 25 divided by 10, which is 2.5. So this is 2.5, 2.5, that is 5. So this is going to be 80. Okay. State the boiling temperature in degrees Celsius of the liquid. Because at boiling temperature, the temperature remains constant. We have already seen that that is going to be 80 degrees Celsius. So this is automatically 80 degrees Celsius. Determine the specific heat capacity in joules per kilogram per gram per Kelvin of the liquid. So let's first check which one is at a higher temperature. So the liquid is supplied with thermal energy at a rate of 810 watts. The beaker has a mass of 42 grams and a specific heat capacity of that. The beaker and the liquid are in thermal equilibrium. So that means the energy supplied by the heater goes into raising the temperature of the liquid and raising the temperature of the beaker. Okay, so if both of them are initially at a temperature of 25 degrees Celsius, okay, so I'll say energy supplied equals to the heat gained by the beaker equal to the thermal energy gained by the beaker, then plus the thermal energy which is gained by the water. Okay, so what is the thermal energy supplied? This is going to be power times time. What is the thermal energy gained by the beaker. That is according to, we know that energy Q is equal to MC change in temperature. So this is going to be the mass of the beaker, specific capacity of the beaker, times the change in temperature. So this is times delta theta, then plus. What is the thermal energy gained by the water? This is going to be the mass of the water times the specific capacity of the water times the change in temperature of the water. Okay, so the energy supplied, what is the time? Let's check the time here. I think this is the time for which boiling starts. I think this is 21 seconds. So the time is 21 seconds. So the energy supplied is going to be power, which is 810 watts, times time, which is 21 seconds. So this should be equal to the mass of the beaker. I think the mass of the beaker is, they want the answer in joules per gram, so I will not change the mass. So that is 42. So this is 42 grams. Specific capacity is given, I think, in joules per gram. Yes. So 0.84 times 0.84 joules per gram. Because this is in grams and this is in joules per gram, the gram has cancelled, so I don't need to worry about that. Then the difference in temperature. The temperature raises from 25 from the graph up to 80 at boiling point. So this is going to be 80 minus 25 plus the mass of the water, which is 120 grams. I will also not change that. Some simply say 120 grams. Specific capacity of water is what I want to find. I know it will be joules per gram because I've not changed the grams. The temperature also raises from 25 to 80, so I will say 80 minus 25. So I'm just going to make a specific capacity of the water the subject. So this is going to be 810 times 21. So that is 1710. Is it? 17010. 17010 minus, I'm going to take this the other side, 42 times 0.84 times 80 minus 25. So that is 2831.22. 2831.22. Okay, then I'm going to divide by 120 times 120 times open brackets 80 minus 25. So that is 6600. Okay, so now I should subtract. I feel like I pressed the calculator wrongly here. Let me check it again. 42 times 0.84 times 80 minus 25. Oh yeah, it is 1940. It's 1940.4. Okay, so let's now subtract. So I have 17010 minus the answer, then divide by 6600. So this is giving me 2.28 joules per gram. So this is approximately 2.28 or 2.3 joules per gram per Kelvin. So this is the specific heat capacity of water. I mean of the liquid. I call it water, but it's just a liquid. The experiment in C, when I leave here water, they will think it is water. It is liquid. Because the specific capacity of water is around 4,200. So let me just use L for liquid. doesn't change anything. The experiment in C is repeated using water instead of the liquid in C. The mass of the liquid used, the power supplied, and the initial temperature are all unchanged. Mass is the same, initial temperature is 25, the power is the same. The specific capacity of water is approximately twice that of the liquid. Specific capacity of the water is approximately twice that of the liquid. The boiling temperature of water is 100 degrees Celsius. On the figure, sketch the variation with time. Let me just give you a clue. So the energy supplied, power times time, this is the same. The energy which raises the temperature of the beaker is still the same. That is M of the beaker, C of the beaker. The change in temperature is what is going to change because the specific capacity of the water is different. Okay, then plus the mass of the water, specific capacity of the water times the change in temperature. This is different and this is different. Because this has remained the same and these have remained constant, it means we shall just only look at the specific heat capacity of water. What is the meaning of specific capacity? First of all, note that the boiling temperature of water is 100 degrees Celsius. So the graph must reach 100 degrees Celsius. But if the power is the same, of course, not the time, the power is the same, and yet the specific capacity has changed. To balance the equation on both sides, the time is going to be greater. So T must increase. The time is going to be greater. And you notice that the specific capacity of water, if you recall, let me see if it is given. The specific capacity of water, is approximately twice. Okay, so specific capacity of water is approximately 4.6, approximately 4.6. If this is constant and the mass of the water has remained constant, yet the specific capacity is approximately twice. Remember, our specific capacity means the rise in temperature, or a high specific capacity means there will be more time to raise the temperature of the given liquid, because specific capacity is like affinity for heat. Water will take more time to raise its temperature because the temperature at which it boils is higher, and water will take more time to raise its temperature. What does that mean? The graph is going to be below the one which is already given. That's number one. And a higher specific capacity means more time. However, the boiling temperature is higher. So it means if the specific capacity is approximately twice, it means the time taken will be a directly proportional to the specific capacity. So the time will also be approximately twice that of the previous case. So if this was at around 21 seconds, then boiling for water will take approximately 21 times 2, which is going to be 42, about 42 seconds. So it means boiling will be at about 42 seconds. So the line becomes horizontal at this point. So I'll draw a line there. Let me get my ruler. So this will be a straight line from 25 because the initial temperature is the same. And then it will become horizontal because at boiling point the temperature remains constant. So I have now a horizontal line here. Okay, so your graph will be somehow like that. Specific capacities is like heat loving. Higher specific capacity means more time to raise the temperature. And remember, the temperature boiling is occurring at 100 degrees Celsius temperature. And since the specific capacitor has almost doubled, it means it will take more time to reach boiling point. Okay. State two basic assumptions of the kinetic theory of gases. I will state almost five. They are almost five. So number one, we assume that particles are in a continuous random motion. Particles are in continuous random motion. The kinetic theory also assumes that all collisions are perfectly elastic. All collisions are perfectly elastic. The kinetic theory also assumes that the duration of collision is negligible in comparison with the time between collisions. So duration of, that is the time for collisions when the particles just collide, the time they stick together is very small. Duration of collisions is negligible. Is negligible compared with time between collisions, or compared to the time between collisions. That is, the time the particles stick together when they collide is very small compared to the time they will take to meet and collide. That is the meaning of that assumption. Then also, particles have negligible volume compared with the gas. Total volume of particles, or the volume of particles is very small compared to the volume of the gas, because the gas always fills up the whole container. So particles have negligible volume compared with the gas. If you get the volume of the gas, because the gas fills up the whole container, and you get the total volume of the particles themselves, you notice that the particles have a very negligible volume compared with the gas. Okay. Also, the forces between the particles, or the intermolecular forces, are negligible, except when the particles collide. So we can say negligible forces between particles, except during collisions. The forces, or the intermolecular forces or interatomic forces, are only appreciable when at that point when the particles are colliding, because in that case they will come very close to each other. Okay. Determine an ideal gas has an amount of substance N. The gas is initially in state X with a pressure 2P and a volume V. The gas is cooled at constant volume to state Y with a pressure P. The gas is then heated at a constant pressure. This was constant volume. Now constant pressure to state Z with a volume 2V. Finally, the gas returns to constant temperature to state X. Determine an expression for the temperature T of the gas in state X in terms of N, P, and V. Identify any further symbols that you use. Okay. So to understand this easily, I will have three states: X, Y, and Z. The gas is initially in state X. Pressure here is 2P. The volume is V. Let the temperature be T1 because it is not known. Then the gas is cooled at a constant volume. So in Y, the volume is still V, but the pressure in Y is P. The temperature is not known. Let me call it T2. Finally, the gas returns at a constant temperature to state X. So here the pressure is not known. Let me call it pressure Z. The volume is not known. I'll call it volume Z. But the temperature is the same, T2, which I'm going to call T, as mentioned before. Determine an expression for the temperature T of the gas in state X in terms of N, P, and V. Finally, the gas returns at a constant temperature to state X. Oh, sorry. X is 2P, V, and T1. State Y, volume is V, pressure P, T2. State Z, constant pressure. So pressure is the same as P, not P2. So this is the same. Constant pressure in Z, it is constant pressure as Y. So it is P. The volume here is 2V, it is not V2. So this is going to be 2V. Okay. Finally, the gas returns to constant temperature. So here the temperature returns at constant temperature to state X. So it means the temperature here is the same as the temperature before. So this is going to be, okay, that is Tz, which is the same as T. So it goes back to stage X at a constant temperature. The temperature is the same as that in Y, okay? So from the ideal gas equation, we know that PV is equal to nRT. So we want to find T. Let's look at the pressure because we are determining an expression for temperature T of the gas in state X. So in state X, the pressure is P, then the volume is in state X. Sorry, the pressure is 2P, not P. I'm using the equation PV is equal to nRT, so the pressure is 2P, the volume is V equals to N times R, then times the temperature T. So if I make T the subject, T is going to be twice PV divided by NR. So this is what the examiner is looking for. On the figure, sketch the variation with the volume of pressure of the gas. This must be a very simple question. So using the analysis that I've given here for X, Y, and Z, we are now going to sketch this graph. At X, the pressure is 2P, the volume is V. Okay, so from X to Y, the pressure becomes P, the pressure becomes P, okay, I'm looking for P, and the volume is constant. Same volume V, but the pressure is P. So I'll put a ruler here. The volume is constant, same volume, but the pressure is P. So it is this point here. So use a ruler to carefully plot this. So same volume as before, but the pressure is P. So this must be Y. So I'll draw a vertical line going down, the arrow points downwards because it is from X to Y. Okay. Then the gas is cooled at a constant volume. That is a horizontal line. Sorry, that is a vertical line with the pressure P. The gas is then heated at constant pressure. Constant pressure is going to be a horizontal line to state Z. So volume is 2V. So the volume becomes 2V, but the line is horizontal. So I'm drawing a horizontal line. Use a ruler to plot a correct graph. So volume is twice V, which is here. I think this is the point approximately. So this is the point. So this is going to be Z. I'll draw a horizontal line here because the pressure remains constant. The arrow points in that direction because it's Y to Z. It said label states Y and Z. So this is Y and this is Z. Okay. Sketch the variation with the volume of pressure of the gas as the gas undergoes the three changes. Then it moves from Z to X. The temperature remains constant, but the pressure and volume change. Pressure changes, volume changes. It is the temperature, so that cannot be a straight line. It is going to be a curve. So I'll draw a curve here, an isothermal, and the arrow points upwards. So that will be the curve there. Because the pressure is changing and the volume is changing, we can't draw that to be a straight line. Okay, so that will be an isothermal. Okay. I'm saying it can't be a straight line. The pressure is changing at the same time as the volume changes. So that is going to simply be a curve, an isothermal curve. So, and this curve must be having an increasing gradient. So this is going to be the graph. At this point here I have plotted 2V against P, and here I have plotted V against P. Here I plotted V against 2P, and then this is a curve. It is not a straight line because both pressure and volume are changing, so that is an isothermal curve. During the changes of state from Y to Z, the increase in internal energy of the gas is U. Y to Z, the increase of internal energy is U. Y to Z. The increase in internal energy is U. Let me see. From Y to Z. Because the gas is expanding, remember, first of all, the total change in internal energy must be zero. Total change in internal energy must be zero. So they have told us that Y to Z, the increase in internal energy is U, and it has been given as positive U. Yet the total should be zero. When I add all, total change is zero. How will it be zero when this is positive U? This should be negative U, so that this is zero, so that the total is zero. There is no way it will be zero, the total will be zero when this is not zero. So if this is positive U, the other one should be negative U, so that when we sum up all of them, the total should be zero. Because when you look at the graph here, we are going back to the initial temperature at X. Initial temperature is the same as the final temperature, so it means total change in internal energy must be zero. So if this is given as positive U, this should be negative U, and therefore this should be zero, so that when we add this plus this plus this, we go back to zero, because total change in internal energy should be zero. So the first column is done. Okay, let's look at the thermal energy transfer to the gas. First of all, let's begin with the work done. X to Y. Let's look at X to Y. X to Y, the volume is not changing. X to Y, the volume is not changing. You know that work done is equal to pressure times change in volume. Because the change in volume is equal to 0, it means that the work done X to Y is 0. So I'll put a 0 here. I'll put a 0 there. Then let me check Y to Z. Y to Z. You see that the volume is increasing. And an increase in volume means negative work done. The work done by the gas is negative because the gas is expanding. It is doing work with the surrounding. So for Y to Z, work done is equal to pressure times change in volume. Okay. But this work done is going to be negative, so I'll put a minus first. So the work done is going to be pressure is constant. The volume is changing from V to twice V, V to 2V. So it is 2V minus V. So this is going to be 2V minus V, which is going to be negative, which is going to be PV, but it's negative because the gas is expanding. So the work done here is going to be P times V. Okay. Now we want thermal energy. So here I'm just going to use the first law of thermodynamics. Of course, I'm not supposed to show the working in the table, but just to show you how we arrive at the answers. So thermal energy. Remember the change in internal energy, delta U, is equal to Q plus W. So here, the internal energy is negative U is equal to Q, which I want to find, plus the work done, which is 0. So it means that Q is negative U. So the answer here is going to be negative U. The answer here is going to be negative U. Here I should use a different. So this is just a working. The answer here is going to be negative U. Let's check the second one. Using the same formula, internal energy is positive U equals to Q, which I want to find, plus the work done, which is negative PV. So when I make Q the subject, it means Q is going to be U plus PV. This is just the working. Internal energy is positive U, work done is negative PV. Then the third one, internal energy is 0 equals to Q plus the work done, which is positive W. So you notice that when I make Q the subject, the energy transferred is going to be negative W. This is just the working. So we have this, have this, we have this, we have that, have this, this, and that. Okay. Part of an electric circuit is shown in the figure. The circuit is used to produce half-wave rectification. So half-wave, that means half cycles are present. The negative half cycles are zeros, they are missing. Of an alternating voltage, the output PD across the 14 kilo ohm resistor is V out. A component is missing from the circuit of the figure. Complete the circuit diagram the figure by adding the circuit symbol for the missing component correctly connected. So of course we want half wave, so I must put a diode here. So I'll join this to that. I'm putting a diode. Okay, because the diode conducts in one direction, the first half cycle will produce an output. The second half cycle will not produce an output. That will give us half-wave rectification. That is the missing component there. A capacitor C is shown in the circuit. State the effect on V out of including the capacitor. Of course, we know that a capacitor in an alternating current or in rectification, a capacitor is used for smoothing. Smoothing means reducing the variation or the fluctuation. So we say that V out is smoothed. V out is smoothed. The capacitor reduces the fluctuations, it prevents the output going to zero. Or you could say less fluctuation of V out. So that is the effect. The figure shows the variation with time t of V in. Okay. Of course, this is constant. The maximum here is constant. So it means the root mean square is always going to be the same. It will not be varying. Okay. The figure 5.3 shows the variation with the time of V out. Determine the frequency of V in. Of course, we know that frequency is 1 over period. So let's check the period from the first graph. The time, of course, one cycle stops here. The second cycle starts. So this is one cycle. One cycle stops here. Here, second cycle is starting. So the time for one cycle is 0.04. So this will be 0.04. So I'll just check with my calculator. 1 divided by 0.04. So this is going to be 25. Show that the time constant tau for the discharge of the capacitor through this resistor is 0.038 seconds. So we know that the relationship between time discharge and the voltage of output voltage is V is equal to V naught e power negative t over RC. Remember, tau is the time constant, is the product of resistance times capacitance. It is R times C. This is the time constant. So I'm just going to substitute the discharge of the capacitor through the resistor. We want to show that the time constant is 0.03 seconds. Okay. So let's check V from the graph and V naught. So this is V naught from the graph, which is the scale is 5 minus, the scale is 2.5 divided by 10, which is 0.25. So this is going to be 5.5. And this one is 1, 2, 3, 3 times 0.25. That gives us, let me check, 3 times 0.25 plus 2.5. So this is 3.25. Okay, so this is V naught and this is V. Okay. Sorry, no, this is V, the other one is V naught. It's the other way around. This is V because the initial is V 5.5 before fluctuation. So this is V. So I'm now substituting the equation. So V is 3.25. This should be equal to V naught, which is 5.5 e power negative. The time for discharge, let me check. Time discharge starts from here at 0.02 and discharge stops here. So the time here is 0.02 seconds, time for discharge. So this is going to be 0.02 divided by the time constant tau. Okay. So first of all, I'm going to introduce ln. So I'll say ln of 3.25 divided by 5.5 is equal to, because I've introduced ln, I will only have the power on the right hand side, so that is negative 0.02 divided by tau. So I'll press my calculator to find tau. Or if you want, you can say tau is equal to negative 0.02 divided by ln of 3.25 divided by 5.5. Okay. So I have ln of 3.25 divided by 5.5. Then I have negative 0.02 divided by my answer. So I'm getting 0.0380. 0.0380. So I have already shown that, and that is in seconds. Calculate the capacitance of C. So since we know that the time constant is R times C, so I want to find C as tau divided by R, where tau is 0.0380 divided by R. I think R was given as 14K, so that is 14,000. So that divided by 14,000, so it's 2.7 times 10 power minus 6. 2.7. Should I add another significant figure? Yes, 2.72 times 10 to the power of minus 6. Of course, we know the capacitance is measured in, sorry about this. Capacitance is measured in farads, so I'll just put here a unit, capital F, or you can write the word farads. The circuit of the figure is modified so that it produces full wave rectification of an input voltage. So if it is to produce full wave, then this fluctuation here will not be there, since V in is having the same maximum, it is just constant. It goes from one constant, positive constant value to positive negative value. I mean constant positive value to constant negative value. Then we shall not have a full wave, we shall just have a straight line, a straight horizontal line. If it was a sine curve, then maybe the fluctuation would reduce, but here we shall have is just a constant, a horizontal line. So I'll simply say, suggest with the reason how V out now varies with V in. So we are saying that since V in has a constant magnitude in both positive and negative directions, if the magnitude was not constant, then the fluctuation will just reduce. But since the magnitude is constant, then we shall just have V out as a constant value throughout, or it will not vary with the time. So since V in has a constant magnitude in both, why do I like writing both like this? In both positive and negative directions, then V out is constant, or V out does not vary with time. Then V out does not does not vary with the time. It is now constant. Because it was constant in the positive and negative direction. When full wave rectification is done, we don't have the half cycles in the first place. We are supposed to have all the cycles, but because it was constant magnitude, then when we have a full wave rectification, it becomes just direct current, constant direct current. So V out does not vary with time, it will be constant. Okay. State with what is meant by a magnetic field. So note that in this example, electric field, gravitational field, and magnetic field were examined. So all the fields were examined. State what is meant by a magnetic field. I said a field is a region of space. So this is a region of space where a moving charge will experience a force. The charge must be moving. A conductor carrying current experiences a force. The conductor must be having a current and at a certain angle to the magnetic field, not part of the magnetic field. Or the poles of a magnet or a magnetic material experiences a force. That is what we call a magnetic field. So this is a region of space where a force acts on, or it is experienced by, or it is caused due to a force, a region of space where a force acts on a moving charge. It must be moving to experience a force in a magnetic field. I can say it is a region of space where a force acts on a current carrying conductor or wire. It's a region of space where a force acts on a magnetic material or magnetic pole. That's what we call a magnetic field. By now, you should be able to differentiate between gravitational field, electric field, and magnetic field in the same paper. A long straight wire P carries a current into the page, as shown in the figure. On the figure, draw 4 field lines to represent the magnetic field around a wire P with the current in the wire. So the cross shows that the current is into the page. Remember, number 1, your teacher must have told you using the right hand grip rule. Imagine gripping your pen, the pen you are using to write in your hands, using the right hand. The thumb points at the sharp end of the pen. The thumb is just aligned with the pointer of the pen, and the fingers are folding around the pen. Your teacher told that the magnetic field due to a wire are concentric circles, and the strength decreases as you move away from the wire. So the field lines close to the wire are closer, and the field lines further away from the wire are more space. So you will draw 4 lines. I'll draw the first one. Let me make the first one to be, you can use a compass to draw something beautiful and uniform. Draw very neat. I'm not too good at drawing, but because I'm drawing on a computer, mine will be not perfectly circular. You can use a compass. So I'll draw the first concentric circle. Use a compass to draw neat circles so that the separation is well seen. So I'm trying to increase the spacing between the first and the second, and I'll also increase the spacing between the second and the third, and I also make the spacing between the third and the fourth even bigger. So if you use a compass, this looks extremely nice. Note that the spacing between the field lines increases as you move away from the wire. That's number 1. Number 2, using the right hand grip rule, make your thumb, which is pointing the same side as the sharp end of your pen, to point onto the page which is on your table at the center of the cross. And if you do that with the thumb pointing onto the cross, holding your pen, the thumb is pointing onto the cross, your other fingers, your four fingers are folding anti-clockwise. That means the field lines must be anti-clockwise. So by the right-hand grip rule, the field lines are anti-clockwise. So the arrows must be pointing anti-clockwise. Those 3 marks are just free marks. You have done this several times in your class. This is very easy. The right-hand grip rule is very easy. A second long straight wire Q carrying a current of 5 amperes out of the page. It is out of the page, that's why you see a dot. Is placed parallel to wire P as shown in the figure. The flux density of the magnetic field at wire Q due to the current in wire P is 2.6 milliteslas. Calculate the magnetic force per unit length exerted on wire Q by wire P. So we know that force due to current carrying wire is given by B. So we want the force per unit length, which is B times I, which is simply 2.6 times 10 to the power of minus 3. That's milliteslas. And the current is 5.0. So I'll just press my calculator. So we have 2.6. Let me start with 5 times 2.6 exponent minus 3. So that is 0.013 newtons per meter. Okay, state the direction of the force exerted on wire Q by wire P. Okay, these are wires carrying current in the same direction. We can use a simple analogy which I expect your teacher must have considered when you were learning this. We want the direction of the force on wire Q caused by wire P. The force on the wire Q caused by wire P. So let's see the force on wire Q. First of all, let's consider the magnetic field caused by wire P. I will draw a field line around wire P which crosses wire Q. By the right-hand grip rule, the field is anti-clockwise. So it means the field here, the tangent of the field here is in that direction. So this is the magnetic field. But here, the current is out of the page. So it means if you use the Fleming's left-hand rule, with your first finger pointing above your page, and the second finger pointing towards you because the field is downwards. If you have your question paper on your table, using Fleming's left-hand rule, just put the elbow on the table. The first finger is pointing upwards because the field is out of the page at wire Q. The second finger is pointing towards you because the field is the first finger is upwards to pointing to the roof because the current is out of the page. You have the page on your table. The second finger is pointing towards you when the elbow is on the table. The second finger is pointing towards you because the field is downwards. The tangent at the field is downwards because the field was anti-clockwise. But at point Q, where the wire Q is, if I draw a tangent, it points downwards. You notice that the thumb is pointing to the left. If you hold your hand, the 3 fingers perpendicular to each other, put the elbow on the table and hold the fingers at right angles, with the first finger pointing to the roof because the current is out of the page. You have the table, you have the paper, the question paper on the table. The second finger must be pointing towards you because at point Q, when I draw a tangent for the field, it is downwards. So the field is downwards. That means the second finger is pointing towards you. When you make the first finger point to the roof and the second finger pointing towards you, the third finger, which is for the force, points towards the left. So let's see the question. The question says, state the direction of the force exerted on wire Q by wire P. The force exerted on wire Q by wire P. let's go back and look at wire P. We want the force by wire P. So again, I will use a different color for wire P. Considering wire Q, I will draw a magnetic field around wire Q which crosses into wire P. So this is the magnetic field around wire Q which crosses in wire P. If I use the right-hand grip rule for wire Q, grip your pen in your right hand with the thumb pointing in the direction of the pointer. Since the current for wire Q is coming outwards, the thumb points upwards above the page. So the fingers are folding clockwise. So this is going, the arrows are going to be in this direction here. And at the point where wire P is, if I draw a tangent, it points downwards. So it means the direction of the magnetic field caused by wire Q on wire P is downwards. Okay. Then, using Fleming's left-hand rule, first finger must point onto your page. Just make the first finger point onto the table, with the second finger pointing towards you because the field is downwards at that point of the wire. The thumb points to the right. So it means the force here is pointing to the right. So the force there is pointing to the right. So the question is, state the direction of the force exerted on wire Q but caused by wire P. So force caused by wire P on wire Q. So wire P on wire Q causes the force to the left. The field of wire P on wire Q is causing a force to the left. The field of wire Q on wire P is causing a force to the right. So the question is, state the direction of force exerted on wire Q by wire P. So it means I consider the field caused by wire P. Let me check this again. Fleming's left-hand rule, first finger is upwards. No, this is not true. I think I changed the first. I used a different. So the field is downwards. Okay. The field is towards you. It is downwards because it was anti-clockwise. Then the first finger points to the roof. The thumb is to the left. So the force here is to the left. I don't think it is to the right. The force here is to the left. The force on wire Q caused by wire P is to the left. The force on wire Q caused by wire P is to the left. That is to the left. Because we are seeing the field of P is downwards here, because it's into the page. Then using the first, making the first finger. Oh yeah, I've changed the fingers, I think. The first finger is the field, the second finger is the current, okay. So first finger is the field, which is supposed to be pointing towards you. Yeah, this was altered. I was wondering how. First finger is the field, which is supposed to be pointing towards you. Then second finger is pointing upwards. Okay, so this is not true. Because the second finger is pointing upwards, this is in this direction. This is the force. If I consider this one, the first finger is the field pointing downwards. The second finger is the current, which should be pointing towards the page. First finger pointing downwards. Second finger, when you rotate the hands for the second finger to point towards the page, the thumb is pointing to the left. Yes, so this is going to be like this. Okay, but essentially two wires carry current in the same direction, the force is repulsive. That is a simple analogy. And if two wires carry current in opposite directions, the force is repulsive. If both of them were carrying current in the same direction, that is into the page, then the force would be attractive. So this is to the right, not to the left. Sorry about that. I had used the wrong fingers. So this is to the right. The first finger is field. Second finger is current. Then the thumb is the force. The flux density of the magnetic field at wire P due to the current in the wire Q is 1.5 milliteslas. Determine the magnitude of the current in wire P. Of course, we know that by Newton's third law, the force per unit length is the same. Force per unit length is the same. The force on wire P due to wire Q is equal but opposite the force on wire Q due to wire P. The force on wire Q due to P is equal but opposite the force on P due to Q. So that is by Newton's third law. So since the force is the same and we have already got the force, I will simply say that 0.1013 is going to be equal to BL. Since the length of the wire is the same, so I'll just say equal, the force per unit length is equal to BI. So I'll just say equal to BI because it's the force per unit length. So I'll say that 0.013 is equal to B, which is 1.5 times 10 to the power of minus 3 times the current I. So I is going to be 0.013 divided by 1.5 times 10 to the power of minus 3. So I'll check with my calculator, 0.013 divided by 1.5 exponent minus 3. So this is giving 8.6 recurring, so 8.67 amperes. Okay, magnetic fields is the most technical part of this syllabus, so you have to be very careful. State what is meant by the Broglie wavelength. Of course, this is the wavelength associated with a moving particle. The wavelength of a particle in motion, the wavelength associated with a moving particle. That is the Broglie wavelength. The figure shows a glass of tube in which electrons are accelerated through a high potential difference to form a beam that is incident on a thin graphite crystal. You must have seen this as a demonstration in your class when you were dealing with electron diffraction. Okay, so after passing through the graphite crystal, the electrons reach the fluorescent screen. The screen glows where the electrons strike it. The figure shows fluorescent screen viewed end on from the right hand side of the figures, that is viewed from this side here. Your teacher must have showed this in a video or in a class demonstration. And this is what is observed. These are concentric rings which are bright and dark, bright and dark. That means they are diffraction patterns. So state the name of the phenomenon demonstrated by the pattern. Of course, this is electron diffraction. The teacher must have showed you this. Electron diffraction. That's electron diffraction. Explain what can be concluded from the pattern about the nature of electrons. Electron diffraction is a property of waves. So it means the electrons that we knew as particles are now behaving as waves. So we can say light and dark regions of concentric circles are diffraction patterns. The light and dark regions of concentric circles are diffraction patterns. The light and dark regions of concentric circles are diffraction patterns. So we can conclude that the electron beam is behaving as a wave. So the electron beam is behaving as a wave. Okay, so the electron beam is behaving as a wave. The electrons in B are now accelerated through a greater potential difference. We have increased the potential difference between the cathode and the anode. On the figure, sketch the pattern that is now seen on the screen in the figure. Of course, first of all, I want you to recall that the Broglie wavelength lambda is equal to h over mv, where mv is the momentum. And you also remember that kinetic energy, which is a half mv squared, is the same as p squared over 2m. You did this in AS. Also remember kinetic energy is equal to the charge times the accelerating PD, which is p squared over 2m. So we have increased the v. When v is increased from the equations, if v is increased, it means the momentum has also been increased. And remember, v is directly proportional to momentum squared. So momentum has been increased. And mv is momentum. So m is inversely proportional to momentum. So because momentum is increased, the wavelength has been increased. Remember from the diffraction grating formula, we know that n lambda is equal to d sine of theta. If the wavelength has been increased, it is because the angle of diffraction has also been increased. So it means the radius of the concentric rings must have increased. So it means here they say the greater potential difference between the cathode. No, the wavelength has been decreased. Because momentum has been increased, the wavelength has been decreased. So it means sine theta has decreased. That means theta must have decreased. So it means the diffraction patterns must have come closer. So we can simply say, okay, I will begin by drawing. At the center, I will have a dot. So you estimate the center and put a dot. Then they say sketch the pattern. So let's first look at the pattern. So we have I'm simply going to draw two concentric because we have this one and this one. So I'll just draw the central dot. Then I'll draw a ring which is very close to the central dot. Then I'll draw the second one which is also closer. Okay, so all in all, I'm just trying to bring the concentric circles closer because the radius, the angle of diffraction has reduced, so the patterns get closer. The patterns will become close. So you can use a compass, have a central dot, the first pattern, you bring the second one closer. The spacing between these two should not be bigger, it should have reduced because we want to show that there has been a reduction in the separation between, or the diffraction patterns have got closer. So now we have to explain this. These were free 5 marks. So I'm just explaining what I've written in expressions here. For example, a greater PD means electrons now have a greater momentum. A greater PD means electrons now have a greater momentum. So greater PD, greater momentum, smaller de Broglie wavelength. So I'll say, so de Broglie wavelength decreases. The Broglie wavelength decreases. That is, we know that wavelength is inversely proportional to momentum. Okay. Then a lower de Broglie wavelength for the same grating spacing in a crystal will cause a smaller diffraction angle. That is, theta will be smaller. So a lower de Broglie wavelength for the same grating spacing, that is for the same value of d, the same grating spacing in a crystal causes a smaller diffraction angle. Causes a smaller diffraction angle, which decreases the fringe spacing which decreases the fringe spacing in the diffraction pattern. So these 5 marks were free. Because the PD has been increased, then there has been an increase in momentum. But remember, momentum is inversely proportional to wavelength, so the de Broglie wavelength has decreased. If the distance, the separation of the interatomic spacing or the separation of the grating has not changed, then it will cause a smaller diffraction angle. Smaller diffraction angle means the fringes get closer, so the spacing, the diffraction pattern reduces. That's why you see I said you will draw fringe patterns which are very close, as simple as that. Remember to use a compass for something to look neat. Medical physics. The table shows some data relating to the properties of air, gel, and body tissue. The data are given to 3 significant figures. Okay, so I will maintain 3 significant figures at least. Show that the specific acoustic impedance of gel is 1.68 exponent 6. Of course, we know by definition Acoustic impedance is going to be density times C. So this is going to be 1200 for gel times C, which is the speed, that is 1400. 1200 times 1400. So that is 1.68 times 10 to the power of 6. So this is 1.68 times 10 to the power of 6. Complete the table by calculating the missing values to 3 significant figures. Use the space below for any working that you need. Okay, so what is missing? For the first row, we need a density. So the first row density is going to be Z over C. Z is 440 for the first row, divided by C, which is 340. I think density of A is 1.29. 440 divided by 340. Yes, 1.29. So the first row is 1.29. Then the third row, we want to find C, that is the speed. C is going to be Z divided by density. And Z is, for the third row, Z is 1.68 times 10 to the power of 6 divided by rho, which is 1090. So 1.68 exponent 6 divided by 1090. That is 1540. 1540, because they wanted 3 significant figures. It's not 1 point, it's 1540. So the answer here is going to be 1540. 3 significant figures. I think the table is full. Okay. Use the information in A to calculate the intensity reflection coefficient for an air tissue boundary. So intensity reflection coefficient IR over I naught, which is given as alpha. We know that this is the same as Z1 minus Z2 over Z1 plus Z2, and this should be squared. The order of Z does not matter because of the square. So this is going to be for Z1, it is the air tissue boundary. So Z1 should be either air, Z2 tissue, or the other way around. So air 140, tissue 1.68 exponent 6. So that is 1680000. No, there are 4 zeros. That is power 6. Minus 440 divided by 1680000 plus 440. This should be squared. Let's check. This is around 0.99998. So we have open brackets 168, 1, 2, 3, 4. Minus 440 divided by open brackets 1680000 plus 440, then square. So it is 0.999 to 3 significant figures, 0.999. Okay, so that is 0.999. Then a gel tissue boundary. Let's look at gel. Gel is 1.68. Boundary this is 1.68. It's like 0. This is automatically 0 even if I don't calculate. But I would say alpha here is going to be Z1 minus Z2. Z1 plus Z2. This is squared. This is going to be 1680000 minus 1680000 divided by 168 0000 plus 168,0000. This should be squared. This gives us 0. So this is 0. Use your answer in B to explain why gel is applied to the skin during ultrasound scanning. So remember, the intensity reflection coefficient means the ratio of the intensity reflected over the incident intensity. So if the intensity, this one means there is no reflection. With the gel, it means there is almost no reflection. That means there is more transmission. Without gel, air tissue, it means there is high reflection because it's 0.99. So intensity reflected is 0.999 incident intensity. That means everything which is incident on the skin is just reflected back. Yet here, it is like almost what is incident on the skin continues if there is gel. So that means without gel, almost all the incident ultrasound is reflected from the skin. Without gel, almost all of the incident ultrasound is reflected from the skin. But we are seeing that with the gel, almost all of the incident ultrasound is transmitted into the body. For diagnosis to be possible. So if there is gel, almost all the incident ultrasound is going to be transmitted into the body, so diagnosis will be possible. Okay. Question number 9. This is nuclear physics and radioactivity. Carbon-11 is radioactive, decays by beta plus emission to form boron. Carbon-11 has a half-life of 20 minutes. Boron-11 is stable. Define half-life. Of course, half-life is the time taken for the number of nuclei in a given sample to reduce to half its original value, or the time taken for the activity of a given sample to reduce to half its original value. So this is time taken for the activity of a given sample to reduce to half its original value. The time taken for the activity of a given sample to reduce to half its original value, that is half-life. Or you could say the time taken for the number of nuclei in a given sample to reduce to half its original value. That is what we mean by half-life. Okay, so a sample contains N0 nuclei of carbon 11 and no other nuclei at time t equals to 0. On figure 9.1, sketch the variation with T of the number of nuclei of boron in the sample. Okay, so first of all, we know that activity is directly proportional to the number of nuclei present. And so if at T equals to 0, N equals to N naught, it means the number of nuclei emitted is 0. So our graph starts from the origin. If the number of nuclei at T equals to 0 is N naught, no nuclei has been emitted. No boron particle or no boron nuclei has been emitted, so small n is 0. Let's consider T equals to half-life. So n becomes a half of N naught. That means n is also equal to a half of N naught. The number of nuclei which has been emitted is a half of N naught. So the graph will pass this point here. Then let's check at T equals to 40, that is second half-life. The number of nuclei which is present is going to be a quarter of N naught. That is what is present. So that means what has decayed is what is equal to the number of nuclei which have been emitted. So N is going to be a quarter N naught. What has decayed is going to be 3/4. So this is going to be 3/4 of N naught. That is, I think, 0.75 N naught. That is what has been emitted. Then let's check at T equals to 3 half-lives, that is 60. N which is present is 1/8, I think, of N naught. So that means which is present is going to be 7/8. What has decayed is going to be 7/8 N naught. So that is the number of nuclei which have been emitted. I think 7/8 is 0.7 divided by 8 is around 0.875 N naught. Let's check at T equals to 80 seconds. Those are 4 half-lives. Number of nuclei present will be 1/16 N naught. Number which has been emitted is that is 1 minus 1/16. That is 15/16 N naught. What is this as a decimal? That is 0.9375 N naught. So we can just plot that. So 0.75, 1, 2, 3, 4, 5. I think this is 0.75 at 40. Then 0.85. 0.85, let's check. I just want the exact number of small squares. The scale is 0.05, so I have 0.875 divided by 0.05. I just want the number of squares. Those are 17.5. 10, 15, 16, 17.5. That is the point. Then I'll check the squares. 0.9375 divided by the scale, which is 0.05. Those are 18.75, approximately 19 small squares, approximately here. So this is going to be a smooth curve. So I'll just draw a smooth curve, something like that. So that is the graph we are looking for. Okay, if it was a graph of number of nuclei present, with the time it will be exponential going downwards. So here the curve is going to look like that. Okay. Explain with reference to the random nature of radioactivity decay why the activity of carbon-11 sample in B decreases with the time. Remember, activity is equal to lambda times n. Activity is lambda times n, and activity is equal to dn by dt. Of course, as time goes on, the number of nuclei present decreases, and it means therefore the activity must be decreasing because the decay lambda is constant, the probability of decay remains constant throughout. So I'll simply say probability of decay is the same for every undecayed nucleus. So fewer undecayed nuclei remaining with the time, fewer undecayed nuclei, or the number of undecayed nuclei reduces with the time. Fewer undecayed nuclei remain with the time, which means fewer nuclei will decay in a given time interval, which means fewer nuclei will now decay in a given time interval. So which means fewer nuclei will now decay in a given time interval. So that is why the activity reduces, because the activity is the number of nuclei decaying in a given time intervals. Because they are now fewer, then there will be a smaller number decaying in a given time interval. State with the reasons whether a radiation detector placed near to the sample of carbon-11 indicates a measured count rate from the sample that is less than, the same as, or greater than. So first of all, I'll consider less than. It can't be the same, but can be less or greater, but most likely less than. Why less than? There are several reasons. The parent nucleus or the daughter nucleus could also be radioactive. There will be self-absorption within the sample, the random nature of radioactivity, the unidirectional nature of the detector. All those reasons as why it can be less. So I'll simply say the measured count rate is less. The measured count rate is less than the activity. What are the reasons? I'll give several reasons here. You want only two, but I'll give more. So there could be some emissions which are absorbed before they reach the detector. So it means the measured count rate is less than the actual one. So we can say some emissions are absorbed before reaching the detector. Some emissions could be absorbed before reaching the detector. The sample emits, because of the random nature of radioactivity, the sample emits in all directions. Here the detector is unidirectional. The detector captures emissions in only one direction. So I'll say the sample emits in all directions. Sample emits in all directions, but the detector captures emissions in only one direction. In only one direction. The detector is unidirectional. There could be some particles which may reach the detector but not cause ionizations. For example, it could be gamma radiations. Some particles may reach the detector but not cause ionization, because the detector relies on ionization. So if a particle doesn't cause ionization, then that count rate is not detected, yet it has occurred. So the measured count rate is less than the actual activity of the sample. Then also you could say the simultaneous arrival of multiple particles could not be recognized easily. If two particles arrive at the same time, then it could be registered once. So simultaneous arrival of multiple particles simultaneous arrival of multiple particles only registers if many particles arrive at the same time, that count rate is registered once, yet the activity is actually higher. The simultaneous arrival of multiple particles on the detector only registers once. So you can also talk about some emissions being scattered within the sample instead of moving towards the detector. Some emissions are scattered within the sample. So some emissions are scattered within the sample without reaching the detector. Without moving to the detector. Okay, so you can choose two of those, but the count rate is most likely going to be less than what really takes place. Okay, and lastly, state Hubble's law. Of course, this is astrophysics and cosmology. So Hubble's law relates to the recessional speed. We know that V is equal to H naught times D. That is Hubble's law. The recession speed, receding is like moving away. The recession speed of a galaxy. Hubble's law only applies to galaxies, not anything in our own galaxy. The recessional speed of a galaxy from an observer recessional speed of a galaxy from an observer is directly proportional is directly proportional to the distance of the galaxy from the observer. I think observe is, I don't know whether it is O somewhere. I think it is ER. So the recessional speed of the galaxy from the observer is directly proportional to the distance of the galaxy from that observer. A star of luminosity 3.8 power 31 is a distance 1.8 power 24 meters from the Earth. Calculate the flux, radiant flux intensity. We know that radiant flux intensity F is equal to L over 4 pi times d squared. So the luminosity is given as 3.8 times 10 to the power of 31 divided by 4 pi times the distance, which is 1.8 times 10 to the power of 24, but this is squared. So I'll check with my calculator. 3.8 exponent 31 divided by 4 pi into brackets 1.8 exponent 24. I have to square this, close the second bracket. So this is 9.33 times 10 to the power of negative 19. So 9.33 times 10 to the power of minus 19. Okay, the star in B is in a distant galaxy. A spectral line in the light from the galaxy is known to have a wavelength of 486 nanometers. That is in the laboratory. The spectral line in the light from the galaxy is observed to have, so you see that the wavelength from light observed from the galaxy is higher than the wavelength of the same light of the same spectral line in the laboratory. So that means there has been a redshift. So the question is, explain why the wavelength observed on the Earth is different from the wavelength that the galaxy is known to have emitted. So we can simply say the wavelength of light from the galaxy increased due to redshift. Wavelength of light from the galaxy increased. The wavelength of light from the galaxy increased due to the redshift. This is because the galaxy is moving away from the Earth. Why is there a redshift? That is, why is there an increase in wavelength? Because the galaxy must be moving away from the observer. So this is because the galaxy must be moving, moving, must be moving away from the Earth. So if the wavelength was lower, then the galaxy would be moving towards. But since the wavelength is higher, then the galaxy is moving away. And finally, determine a value for the Hubble constant H0. A value for H0, Hubble constant. So we know that Hubble's constant H0 is equal to V divided by D. So first find V. So we know that from the redshift, delta lambda over lambda is equal to V over C. So I'll make V the subject. V is going to be equal to change in wavelength, which is 492. The other one is 486 divided by the expected wavelength in the laboratory, which is 486. That's the fractional change in wavelength times the speed, which is 3 times 10 to the power of 8. I've just made V the subject by substitution. So I'll press my calculator. 492 minus 486 divided by 486. Don't ask me why I have not changed the wavelength, because I'm dividing nanometers by nanometers, just cancelled out. Then times 3 exponent 8. So this is 3.70 times 10 to the power of 6. 1, 2, 3, 4, 5, 6. Okay, so that is V. So now I will find H naught as being equal to 3.70 times 10 to the power of 6 divided by D, which is the distance, that is 1.8. The distance of the galaxy is 1.8 times 10 to the power of 24 times 10 to the power of 24. So I'll just press my calculator, divide by 1.8 exponent 24. So that is 2.05 or 2.06 times 10 to the power of minus 18. Or you can write 2.1 times 10 to the power of minus 18. Okay, so I think that marks the end of this paper. I took an extra 30 minutes because I gave a lot of explanations and gave several alternative answers. I hope this has saved a lot. I hope I've tried my level best to explain this paper. If you have any comment, any question, you can always send me a message, write a comment on this video. Until next time, bye bye.